Welcome back, folks. So today we're going to start on another beginner's project sponsored by our pals over at PCBWay. Today we're going to look at resistor capacitor networks. In particular, we're going to look at these four audio frequency filters. We're going to look at a low pass filter, a high pass filter, a band pass filter, which is basically just a high pass filter followed by a low pass filter, and a band attenuate or cut filter or notch filter, however you want to call it. And this one's set up in a slightly different way, and I'll explain that in a minute or two. But before we get too far into all of this, I'd like to give you a word about our sponsor, PCBWay. Just thought I'd show everyone my personal journey with PCBWay. If you've been watching my channel, you know that they are a sponsor of mine for some of the little projects I do. But long before that, long before I started doing these, I was using PCBWay to realize my designs, put my projects into form. It's going back quite a while. This one here, I can't even remember the name of the account I had from when I got this done. But I was more or less a beginner laying out PC boards. It's not very well laid out, but the PC boards are excellent. And I get them to build some platform-specific prototyping cards as well, for those times when I can't wait the couple of weeks it takes to get a board in from PCBWay and I have to get something out. I have these made up as well, so I can pop something together pretty quick. And they're designed to fit into some of the projects that I've come up with along the way. Some of them have been fairly simple, things like this. This is like a little Arduino thing, and this is a little power supply that fits into a breadboard. And some of them get a little bit more complex, like this system here, which is a computer, a stackable computer. So you can have the computer on the top, and then you can stack various boards underneath for various functions. And do even more complex things, like this hexadecimal terminal. Go on up to even more complex things like this computer here, which has got its own motherboard built into it, and can take some pretty amazing cards on it that quite expandable. And that here's a perfect example that if 5 of these boards done up for $5, and I made a mistake on this one, so I got them to make up another one that doesn't have the mistake on it, and I'm going to do a project based on this coming up. Yeah, so I mean, like for $5, if I absolutely have to use one of these, I will. Most of the time I do have a couple of weeks to wait for the boards to come in. But that's it. That's my personal journey with PCBWay. They've been in my life for a long time, and they've helped me bring many projects to reality. Excellent people to do business with. So let's go and have a look at the low pass filter first. So here's the low pass filter. We're going to be using a 10K resistor and a 6.8 nanofarad capacitor, and it's going to have a knee frequency. Now that the knee is here, so that's a 3D point. Let me show you that. So we've got a 10K resistor here, 6.8 nanofarad, and that gives us a minus 3 dB cutoff frequency of 2,340 hertz. So what I mean by 3 dB, well, whether it's a low pass filter or a high pass filter, that minus 3D point is down from the maximum value. So in either case, whether we were using this as a low pass or high pass filter, this would be the 3 dB frequency for this particular combination of resistor and capacitor. And this is the formula here. The frequency is equal 1 over 2 pi RC. And that's the way we've shown it here as well. So 1 over 2 times pi times R times C. And that gives us a response like this. At some point along the line, as increasing frequency, the filter will start to reduce its output. And why does it do that? Well, basically this capacitor, you can think of it as a frequency dependent resistor. So if we go over here, we enter the 6.8 nanofarad and enter the frequency that we're interested in. It could be, let's try 10 hertz. We can see that resistance is 234 kilo ohms. But if we get up to much higher frequencies, let's say 20 kilohertz, that drops down to about 1200 ohms. So you can see as the frequency gets higher and higher, that capacitance is going to get lower and lower resistance. And what will that do? Well, it basically starts acting like a voltage divider. So in the ideal situation where we have a zero impedance source and infinite impedance load, and we're going up to a high frequency limit, the highest we can go, that's going to look like a short. So basically you'll get nothing out. No matter what you put in, you'll get nothing out. At the low frequency limit, it's going to look like an open circuit. The resistance will be so high, as we saw at 10 hertz, it's 234 kilo ohms. So in the ideal low frequency limit, let's say at 1 hertz, it would look like this. So you'd get whatever you put into it, you'd get out of it. And the same can be said for the high pass filter. In this case, we're just dealing with a different value here. We're putting in a 0.33 UF or 330 nanofarad capacitor and 1K resistor. And then we do the calculation, we get about 482 hertz. And this is what it looks like at the frequency limits. So the low frequency limit, this is open and you get nothing out. At the high frequency limit, this is basically a short and you get everything out that you put in, and that's represented in this curve here. And again, that frequency is around about here, where you're about the 3 dB point, or what they call the knee point. At the center of that curve is where the 3 dB point is. Now our bandpass filter here, that's just essentially a high pass filter followed by a low pass filter. And you can see here our high pass filter begins to come in at a lower frequency at 480 hertz, and then it'll run along at the maximum output until it reaches the low pass filter, which will kick in around 2.34 kilohertz, and then it'll cut off. And here, if you look at the low frequency limit, the high frequency limit, and now the center frequencies, because we've got two filters involved, you see the low frequency limit is pretty much like what it was for the high pass filter. It's going to have this other resistor in here, but that's really not of any consequence considering we have a infinite ohm load. And then the ideal high frequency limit is going to be pretty similar as well. This capacitor here is eventually going to look like a short circuit and we're not going to get anything out. Now, however, in the center frequencies, this is what we'll have. Since our source is zero impedance, or in reality very low, and our load is infinite, or in reality very high, we're going to get basically out what we put in. Now, the way we're going to test this out, of course, we're going to use a fairly decent signal generator. It's got a 50 ohm output and a fairly decent oscilloscope with a 10 meg ohm input. So we're going to reach pretty well, as far as these values are concerned, pretty well ideal conditions. There will be a little bit of difference, but not much. And here's the band attenuate filter. Now, we'll get over to this part here is the center frequencies. The interesting thing about why I chose to do it this way. So again, we have the variable resistances here that vary according to frequency. So with the low frequency limit, this pretty well going to be open. This is going to be open. So we'll have input going through a 10K resistor and coming out. Let's talk about the real case here with a 50 ohm source and a 10 mega ohm output. That 10K resistor is going to be meaningless. So we'll get out exactly what we put in. The high frequency limit, this will pretty well look like a short, so will this. So this is basically the circuit we have. Again, this 1K resistor is not going to mean anything. What we get out is basically what we put in. In the center frequencies, this will be open and this will be shorted. So this will already have gotten into a very low ohms and this won't have started to change significantly yet. So we basically have a 10K resistor in series with a 1K resistor, which is our voltage divider. If we look at the voltage divider here, we've got a voltage source, just to say it's 1. And we have a 10K resistance at the top, 1K resistance at the bottom. Our voltage out is going to be 0.091, what we put in. And if we go over to this decibel calculator, 0.091 voltage ratio, it's going to give us a minus 21 dB cut. And at center frequencies, we should be getting around about minus 21 dB out of this filter. Again, that's under ideal conditions, though we should be getting pretty close to this. And this is kind of what it looks like. When it hits this 480, it'll start to go down and it'll stay down near the bottom for a little while. And then when it starts getting close to that 2.34 kilohertz, which should be up here, it'll be back up to the top again. We can adjust this. So if we had 10K top and bottom here, our output would be just down 6 dB. Or we could have any value you want here. In fact, you could put a variable resistor in here, and this would be the wiper of the variable resistor or potentiometer. And you could have a variable filter here where you could change the center frequency as much as you wanted. So let me show you the circuit I came up with for this. And we didn't need to put in the bandpass filter because that's basically just a high pass filter followed by a low pass filter. So that's what we've done here. We've put a little jumper in here so that we can connect the output of the high pass filter to the input of the low pass filter, and then put our input in here and our output here, and we'll have our bandpass filter. And here's our band attenuate filter. Very simple circuit, but these are very important circuits. And it's good, a really good idea if you want to learn and grow in electronics to understand how capacitors work and how they interact with resistances and stuff like that, and what you can use them for, because anything beyond just simple, straightforward amplifiers like we've done already, but anything like oscillators, active filters, are going to require you to understand some of the basics of this sort of stuff. So let's go and look at the circuit board I came up for this. It's very simple. In the typical fashion, what I've done here, I've laid it out in units. So this up here is the low pass filter. This here is the high pass filter. Here's our little jumper to make our band pass filter. And then here we have our band attenuate filter. Again, I've used very nice wide traces to reduce any chance of introducing inductances. Although at these frequencies, at all these frequencies, it's not going to matter. And I put a ground plane on the back. It's a very good practice. I didn't have to do it in this case, but I do it all the time. I just route things so that I can have the best possible ground plane. So I've sent this board off to PCBWay and going to get them to make it for it. And when it comes in, we'll build one of these up and we'll test it out. And we'll show you those curves. And we'll see some of the differences between idealized design and reality. Okay, folks. Well, thanks for joining me today. And we'll see you in the next video, probably in a couple of days or so. Bye-bye now.